Hi and welcome to video 5 in this video series for Unit 4 Topic 2 of the Specialist Maths curriculum, and we're going to be looking at some applications of differential equations. So if you're interested, there are my learning goals and success criteria for this area, and of course the textbook references for the Cambridge text that I use at my school. So differential equations, first of all, let's just talk a little bit about the general applications you might see, and I've got some links here to that textbook exercise as well. So you might see some growth and decay, length, area, volume problems, financial contexts, Newton's law of cooling, which we'll go through in later videos. Radioactive decay is quite common, or population growth is quite common. Logistics population growth model is also a very specific example, which we'll go to in a later video. And there's heaps of others. You just got to read the question and understand whether it's asking you for the solution to a differential equation from the information given. There are many cases and situations, and I'm going to cover some of these in examples. So the next 6 videos that follow are going to go through a whole bunch of different examples and situations to try and cover off on as much as we can. So let's have a look at a basic one first, example 1. And there's a bit of a process defined there as well, which is pretty generic. It's a process I follow. I've arbitrarily numbered it, but I think it's a pretty good process to follow. So example 1, the number of bacteria present in a sample of milk increases at a rate that is proportional to the number present. If the number of bacteria doubles in half an hour, calculate how long will elapse before an initial number of bacteria of 1,000 will become 1,000,000. So this question gives us a little bit of information. First of all, it tells us that the population at time 0 is 1,000. Now we don't know whether that is actually at time 0, but it's our defined 0. We're defining that time starts when we have 1,000 because that's the context as provided in the question. When time actually starts in this situation, we don't really care about. We want to know what t is when the population is 1,000,000, but we'll get to that later. The population at half, that's half an hour because it doubles in half an hour. So the population at half an hour is 2,000, and that will be important as well. There should always be some extra information, some sort of data point somewhere, because you're going to end up with constants that you need to solve for. Unless it's a really general question, you're probably going to end up with constants, so just be wary of that information. So step 1 is to define our variables, which I think we can agree we've done here already. P is the population of bacteria, N is the number of hours. Step 1b is to set up our differential equation. So I've written down some initial information. Now we're told that the bacteria present in a sample of milk increases, so we're talking now about a differential equation, at a rate, so that's dt, or dn, because n is our number of hours, that's proportional to the number present, and the number present is our p. So dp dn is equal to, or is proportional to p, which means of course that dp dn is equal to Kp, some constant times P, and K seems to be the constant we typically use in proportion relationships. Now, if the PDN is equal to Kp, we can solve this differential equation using the knowledge we know. We don't know anything about rates of change yet, so the best we can do is solve it, and then we're going to end up with 2 constants, a K and a C, and we'll have to solve for those 2 constants separately. So let's go through the situation of solving. I'm going to write this down as 1 over P dp is equal to k dn, and then I'm going to integrate both sides. So that's my rearrangement. Now the integral of 1 over p is log p, and the integral of k is kn, remember n is our time, plus c, some constant c. Now technically I've integrated both sides, so there's a c on both sides, but I can combine them together. If the c on this side end up being contextually minus 3, and this one ends up being contextually minus 5, well then this one with the c on just one side will end up being minus 2 because I've combined them together already. So it doesn't matter if we only have c in one place. Now I'm going to rearrange this because I really do want population in terms of time, and so p is equal to e to the power of kn plus c, and I'll do this once, but I won't do it every time, so you need to start seeing this pattern. But e to the power of kn plus c is equal to e to the power of kn times e to the power of c, and then we typically let a equal e to the power of c, and we get a e to the power of kn. That's a pretty standard rearrangement, and this step here you don't normally have, or you don't have to have at least. So just keep that in mind. Now we've got the population is AE to the KN, and we know at N equals 0, P equals 1000. Now with a really standard population model like this, you're going to see that A has an obvious value, but it's always nice to show why. So we know at that time, 1000 is equal to AE to the K times 0, and e to the k times 0 is e to the 0, and e to the 0 is 1. So we get a times 1 is equal to 1000. Hence, a equals 1000. In a model like this, a is always our initial population. But only in a model like this. You have to be careful, because if the model changes slightly, or when we get to logistics curves, a is not necessarily our initial population. So just be careful. So p is now equal to 1000 e to the kn. We also know that at n equals 0.5, the population is equal to 2000. That's our doubling rate. So we get 2000 is equal to 1000 e to the 0.5 n. I suspect I'm going to have to make some more room in a minute. And rearranging this, 2000 divided by 1000 is 2 equals e to the 0.5 n. Taking a log of both sides, I get 0.5 n equals the natural log of 2. And n equals 2 log 2. And I could work out the value of that, but you know what? We're better leaving it exact. So let's leave it exact. Now, creating a little bit more space, I get n is equal to 2 log 2, so my population is equal to 1000 e to the power of 2 log 2n. And I can now substitute in some information to determine when t is equal to, or when population is equal to 1 million. So at p equals 1 million, let's have a look at what we get. 1 million equals 1000 e to the 2 log 2n, which means that 1000 is equal to e to the 2 log 2n. Take a log of both sides, I get 2 log 2n equals natural log of 1000, and therefore n is equal to the natural log of 1000 over 2 times the natural log of 2. And if I pop that in my calculator, I get about 4.98, and we're talking hours. And this actually suits what we'd expect, because obviously we know that population growth happens pretty rapidly at a bacterial level, and this is growing at a fairly rapid rate. So to get from 1000 to 2000 in half an hour, but get to 1 million in 5 hours, well, that's not uncommon for exponential growth. So there we go. There's our solution to example 1. And I'm going to quickly run through example 2. And I say quickly, but example 2 is a bit hefty as well. So I'll run through it, and if you want to stop the video and have a break now, then it might be a good idea. So here's the question. It's to do with a context to do with Torricelli's law, and Torricelli's law is there, and we've actually been given, so you might know nothing about Torricelli's law, and this can scare some people off from questions, but we've been given the rate of change. We've been given the differential equation, and we've been told K is a constant to do with viscosity of liquid and cross-sectional areas, but that doesn't matter to us. We know A is also a constant because A is the surface area of the liquid. So A and K presumably are constants that we're going to be looking to find. Now, here's how this question works. And there's a little bit of a trick at the start, because we have two unknown constants. And so I'll just write down as this. H is the one thing that's a variable, and we know dh dt. So I'll just read through this. It says, use Torricelli's law for a tank that is cylindrical, initially full, and that has a height of 1.6 meters and a radius of 0.4 meters. Use K equals 0.025, construct an appropriate differential equation, solve it, and find how many seconds it will take for the tank to empty. Okay, so it'll be empty. So when is H equals 0? That's what we're after. How long will it take for the tank to empty once we solve and build this differential equation? But we can work out, we're given K, and we can work out A, the surface area, because we know the radius. So let's go through that process now, and develop our constant. So negative k over a is the constant component here, and that's going to be equal to, and I'll be working on my calculator, it's going to be equal to negative 0.025 over area, which is, that's the circumference, pi r squared. But the radius is 0.4, so pi times 0.4 squared. And so I get this, 0.025 divided by pi times 0.4 squared, and I get negative 0.049736, give or take. Okay, bit of rounding there. Now I'm actually a bit worried about rounding too early, so I'm going to do something that's a little bit tricky here, and I'll put it in orange just so you recognize it. I'm going to let w equal negative k over a. Why w? I don't know, I just chose it. But it will mean that I don't have to round until later. So I've got that answer on my calculator now. I'm not going to touch it. I'm going to keep it as my answer. I'm not going to throw a rounded value into my differential equation. I'm going to write my differential equation instead as dh to t is just equal to some constant times h to the power of a half. And now I'm going to solve this differential equation. So I get h to the power of negative a half dh equals some constant dt, and that constant's about negative 0.049. And then I'm going to integrate. I get h to the power of a half over a half, so I've integrated there, is equal to wt plus some constant. Now I know w, I just don't know c, so this gives me 2 times the square root of h is equal to wt plus c. Now I'm going to go back up and look for what else do I know. So I could work out, because I've got the initial depth, the initial height, I could work out the initial volume if I needed to, but in this case I don't. But I do have the initial height of the cylindrical tank, and that's at time 0. So I know that at t equals 0, h equals 1.6. And I'm just check I'm using meters. I used meters earlier, so I'm happy with that. And so I get this, 2 times the square root of 1.6 is equal to w, which I know, times 0, so it doesn't matter that I know it, c. Now the square root of 1.6 is not going to be an overly happy number, so I'll just grab my calculator and get that out, but I might end up leaving it as the square root of 1.6 because that will be a nicer number to deal with. So yeah, so it's not a nice number, 1.2649. I'm just going to leave it as the square root of 1.6. C is equal to 2 times the square root of 1.6. And now I've got this. 2 root h is equal to wt plus c, but c is equal to the square root of 1.6, and I know w. Now I want to know, when does h equal 0? Probably don't need a comma there. And so I put in my h equals 0, I get 2 times 0 equals wt plus 2 root 1.6. And then I could subtract the 2 root 1.6. So I'm a little bit worried, I've got a negative here. I don't want a negative time, but then I recall that w is a negative value, so that's okay. Over negative w, over w, which is a negative number, is equal to time. And so now what I can do is throw those values in, and it should give me hopefully a nice and appropriate answer, and I get this, t is equal to 50.87. And now I just need to take a second. I've done height in meters, and w was in terms of area, and k, which was a constant, so I haven't actually got a unit here. So I'll just go back into the question and go t in seconds. So, and that's good because seconds makes sense. So t's in seconds, and that's the answer to that question. But just notice in this question, 1, eliminate the context. You don't have to worry so much about the context. And 2, take your time to consider how you do your rounding throughout the question. Keep your values exact if you can, or better yet, make life easy by introducing another constant that combines complex values and allows you to just maintain that accuracy throughout. All the best.